Paracetamol is a medicine commonly used to relieve mild pain. Traditionally, paracetamol has been made in a 3-step synthesis from phenol. Name the mechanism for the reaction in step 1. So if we have a look at step 1, we can see that we're nitrating a benzene ring. So our mechanism involves the pi bond attacking a positive NO2, which would be accepting electrons. So we're going electrophilic and we're swapping it for a proton, a hydrogen ion. So electrophilic substitution. Equation for step 2, where an aromatic nitro becomes an aromatic amine. That's using tin and conc HCl. And that's a reducing agent. If you remember this equation, if you don't remember it's 6 H's, you know it's a reducing agent, H in square brackets. You can see that 2 oxygens have had to come off as waters, so there'll be 2 waters, and then if you balance the hydrogens, you get the 6. In theory, either ethanoyl chloride or ethanoic anhydride could be used in step 3. Complete the mechanism. We're showing the phenol as an R group. So the double bond has opened up to become a single bond. The electrons have been moved on to the oxygen. So we've got a lone pair. Chlorine hasn't done anything. The N of the amine has attacked and so lost its lone pair. So we need this intermediate with 1 lone pair, 2 charges, and then we're going to add 3 curly arrows. So it's the 1, 2, 3 of nucleophilic addition elimination. So we've got 1 lone pair, 2 charges, and 3 curly arrows. So we're going to reform the double bond, kick out the chlorine, and deprotonate the amine group. So we've ended up with reforming the double bond, losing the Cl, keeping the R group, keeping one of the hydrogens, and we've eliminated H plus and Cl minus. In practice, ethanoic anhydride is used rather than ethanoyl chloride. Give one reason. So one of the reasons is ethanoyl chloride forms toxic HCl fumes. So we start the word chloride there, ethanol chloride. Ethanol chloride is more corrosive. That's another one. Ethanol chloride is vulnerable to hydrolysis. These are all different reasons you could give. So that means it basically reacts, turns into a carboxylic acid, so no good to us. These are all good reasons. Avoid things like cheaper or more expensive. They're not good answers. In step 3, another aromatic product is formed, as well as paracetamol. Draw the structure of one of these aromatic products. So let's just go back, find step 3. It's a long way back. So we can see here that we acylated, we added the acyl chloride group onto the amine. So there is another option. It is possible that instead of that acyl chloride, the lone pair on the nitrogen attacking, what if the lone pair on the oxygen did the exact same reaction, because alcohols can do the nucleophilic addition elimination. And so the amine remains as an amine, but the lone pair on the oxygen does the reaction, it loses its H, and we acylate the alcohol group there. Oh, there's another option in that both go at the same time, so you have both the ethanoyl chloride groups on both the top and the bottom. Chemists have recently developed a 2-step process to produce paracetamol from phenol. In the first step, phenol is oxidized to hydroquinone. You can see that reaction there. In the second step, hydroquinone reacts with ammonium, so an ammonium ion is an NH4, ethanoate, CH3COO minus. Okay, so if we put those together, CH3COO NH4, that would be our ammonium ethanoate. And if we balance this out, we can see 1 where things have gone onto our structure. So we're just having a look at our formulas. We've used this N. So counting up atoms changes have all happened around about this point here, haven't they? So we need to figure out what's been lost and just do some adding up. The C's have all gone in. We've lost, we had 1, 2, 3 O's and now we've got 1 O. So we've got 2 more O's to go in. We had 3 CH3, a CH3. We had 4 H's and we've got 5 H's and we've now got 1. 1, 2, 3, 4, 5, and we've got 1, so we've got 4 H's. We look at that, that's going to be water. And always, a good guess is always water, and then try to balance it. Calculate the mass of hydroquinone needed to produce 250 kilograms of paracetamol. So we're going to assume 100% yield. So let's do the number of moles of the hydroquinone. So mass. Oh, we can't do that because we don't. That's what we're trying to calculate. Let's do the number of moles of paracetamol. So mass 250 kilograms into grams over the MR of paracetamol. So we need to go back up here and we need to add up the MR of paracetamol. So we have got, in our ring, we've got C6H4 because we've got 2 substituents. And then we need to add an OH. So this bit would be 76, this bit would be 17. Then we've got the NH, 15. We've got the CO bit, 28. And then a CH3, 15. So if you get your calculator and you add up those bits, you get 151. So 1.656 times 10 to the 3 moles. So assuming 100% yield, then the number of moles of hydroquinone is the same. And so then mass is Mr. Moles, so 110 times that. .82 times 10 to the 5 grams, and it wants it in kilograms, so divide by 1,000, and we're going to get 182 kilograms.